Thanks, everybody. I work at Techtronix. Techtronix, if you don't know, sells stuff like oscilloscopes and all sorts of sources, arbitrary wave generators, arbitrary function generators. We do a lot of video stuff. So I'm in the software group. However, we develop software for an actual physical thing. Now, we like to do stuff that other software groups do. We do like Agile, right? We want to do continuous integration. We will still want to do continuous deployment. We want to do all those things and all those best practices that we've talked about. But we also have this kind of, I don't want to say it's a boat anchor, but we have this physical product that we have to kind of work with. Because that's the thing we're selling. We're not just selling software. We're selling software on a product, and the customer gets the full package. So I'm going to be talking a bit about kind of our journey on the last oscilloscope we did and how we implemented continuous integration with a physical product. So I'll briefly describe what the problem was we had. I'll talk a little bit about the stack that I used to solve the problem. I don't think that the tools we necessarily used were as important as the journey we kind of took. So I'll briefly highlight those things. They should be familiar to everyone, but they're kind of a sub-point really, because they could have been done with other tools. I'll briefly highlight what we viewed continuous integration as, especially considering that we had hardware with it. And then the final three things I'm going to talk about are probably the most important. Minimum accessibility, abstract communication, and dynamically reconfigurable hardware. These are concepts that I'll introduce as we go, but they were really key concepts that we had to overcome and implement in order to do continuous integration with our product. So, does anyone not know what continuous integration is? We've been talking about it for a long time. Continuous integration with software makes a lot of sense. We're constantly making changes, we're constantly pushing changes, we're testing those changes, making sure they're good, and then we're integrating them in together, right? All these engineers from all over the world are constantly merging code for this product that we're developing, and we need to make sure that it's good so that way we don't break somebody else. So continuous integration in and of itself with embedded software is not unique with that respect. However, the embedded software development is extremely influenced by the hardware that we're developing. Hardware has its own development track that it does. Some agile principles and things like extreme manufacturing have happened to try and bring manufacturing and hardware processes forward into the future, but it doesn't always work out that nicely, and it's not as agile as you can be with software. So we kind of joke at the office and we say that we don't really do Scrum. We kind of do this weird Scrum fall because hardware development is still kind of doing this waterfall style. We're going to design it, and then we're going to build prototypes, and then we're going to iterate over that, and then eventually we're going to do final review and ship it, right? So software has to iterate over those key milestones in hardware. However, as a software group, we still want to do things like continuous integration, right? So that is the scope that we developed. That's an MSO5 series. There's a few engineers in here who worked on it. What we really needed to do, the problems that we had to solve with our continuous integration setup. As a part of the software group, we're writing the application that runs on this product. So the software that's on the display, right, that's what I actually kind of care about testing. However, what I really need to do to prove that it's correct and prove that it's the full customer experience is I need to prove that it actually works on the oscilloscope. I have to test my software with the oscilloscope. I could test it in a container, I could test it kind of isolated from the hardware, but at the end of the day, there's ASICs on that, there's special hardware, there's special drivers, there's a lot of special things about that physical setup that I really could not virtualize. Another thing about setting up continuous integration for this is I really want to be able to accept arbitrary configurations. So if you look at this device, you don't have to know much about it, right? But there's some types of inputs that you can accept, some types of accessories and peripherals, probes, right? Different licenses, different things that I could put on there that from customer to customer, that scope could be completely unique. They could have their own setup, unlike another customer, that I need to be able to identify and be able to test those things, right? Another thing about working with physical hardware is that it's not easy to physically change them in the lab when you're trying to automate stuff. If I have probes and things hooked up to it, or I have certain licenses or different things that make that box behave differently, it's very difficult for me to automate programmatically changing that setup. I can't program a different probe onto that thing. I can't program a different peripheral. I have to have somebody physically adjust it, right? Because that's part of the full interaction. I need to see that a different probe can work, that a different probe can take a different measurement, stuff like that, right? So that's an important aspect, an important challenge that we had to try and work around when we were thinking about how do we do continuous integration? How do we test all these different things when we're obviously limited physically by what the scopes are set up as? So, like I said before, just very briefly, this is the infrastructure that we used. We used a combination of Jenkins for running our automation jobs. We used Bitbucket for version control, so Git, and we also used the rest of the Atlassian stack, so Jira as well for issue management and stuff like that. We used vSphere, vCenter, really, for virtual machine management. So vSphere is a hypervisor where you can spin up virtual machines and have them organized and collected into there. And then we also use Chef. Chef is a configuration management tool. We use Chef to kind of orchestrate our kind of fleets of VMs that we were using in vSphere. How these things work in concert, I'm going to get to in a slide or two so you can actually see how we were using these tools to address our problems. But just as a really brief highlight, these are the things we were using. So this is a big, nasty diagram that describes how we did continuous integration. There is a lot of pathways, a lot of conditional statements, a lot of blocks in here. This describes all the way from the individual developer, how they work on and test their code individually, go up into team review, how this works into things like feature streams, and eventually how do they contribute to the larger product on the whole. And then once it bubbles up from that, it goes into how does it kick into our automation system, how does it trigger jobs into Jenkins, what types of tests do we do, what types of tests do we care about passing, what ones don't we care about passing, and ultimately what does it mean to deploy a build, right? So that's the whole pipeline. And really, you could summarize that whole chart into how do we build, how do we test, how do we integrate, and how do we deploy, right? So, did you want a picture? Did somebody take a picture? You want to go back? You good? Okay. So, now we're going to get into what we actually did. How did we actually do continuous integration with these oscilloscopes that we were developing? The very first thing that we had to do is we had to decide on something called minimum accessibility. So minimum accessibility is this idea that I want to take a customer product, my oscilloscope in this instance, and I only want to enable the minimum set of things it takes to do continuous integration. The caveat there is that I may not have to do anything extra. If the user interfaces, tangible, programmatic, or otherwise, if those already exist and I can execute my tests and I can deploy my code to those physical instruments without doing anything extra to them, then I have achieved minimum accessibility. Okay, so only the very minimum thing that I have to do to make that work with Jenkins, right? So if I have a job in Jenkins that says the latest build, the 1.0 code is done, I have to have a way to deliver that code to the oscilloscope, the 1.0 code, have it install, and have tests execute against it. If I could do that purely through customer-facing interfaces, perfect. I'm done. I didn't have to do anything. I didn't have to add anything. I don't have to add something weird like SSH. I don't have to keep debug consoles. I don't have to do anything. I can keep it in a purely customer-facing state. However, sometimes I can't do that. So for these oscilloscopes, as a good example, when I want to install the latest build on it, a customer would be expected to get the binary from the website, put it on a flash drive, plug it into the scope, and update the scope that way. That's how the customer is going to do it. I am not going to have robots in my lab flying around little USB drives. That's because they're not going to give me the budget to do it. But I'm not going to have that, right? So I need to enable something extra because I don't have a programmatic way. I don't have a built-in customer way to do that that is reasonable for continuous integration to work. So I add SSH. I add SSH. Only explicit exceptions should be added. I added SSH to this oscilloscope. That's the one thing I added. And I added it for a very explicit reason. I want to be able to install the application without having to physically plug in a USB drive. Did I add a risk? Yes. It's no longer a customer-facing scope. There is something absolutely different about it. Do I understand the risk? Yeah, I do. I added SSH. That means that it's accessible in a way that a customer will never be able to access it. However, I've made that explicit exception, and I understand what I've done, and I understand why I did it, right? If you look at, this is kind of a block diagram. You people in the back probably can't really see that because I can kind of barely see it up here. So if this is my oscilloscope, and we're talking about user interfaces that are accessible to a user, I have, say, some tangible user interface. I have buttons. I have dials, right? I may have a touch display. I can hook up probes, which are other little devices, right? I can communicate with this oscilloscope over a programmatic interface. So that communicates with like Skippy commands or over TCP/IP or USB TMC, right? Like, so the customer has a lot of different ways that they can get at this oscilloscope, which is great because that's how we can test it. We can execute tests that operate over, the TCP stack and do things remotely that way. That's great. I don't have to use SSH, right? So we boil back down again to I have added a very explicit exception. I've added SSH, and I do it for one very particular task. I don't get crazy and I don't start saying, well, we've also got SSH, so we can do these other crazy things. No. You insist and enforce that the tests use the interfaces that they should, because then you also get the benefit of testing the interface that a customer is going to get. When you decide on minimum accessibility, because all of you may not be developing oscilloscopes, it's kind of a niche market, I think. But you may have some other device that you're working on. You could have like this microphone, or somebody else is telling me about hearing aids out in the lobby, right? You could have some other physical device that you're writing embedded software for. So you could have some questions, and maybe this could work for other things too. I'm not really sure. I've only thought about it from an embedded software perspective. But you should ask yourself, what interfaces are available to a customer? What can they already do? Do they have a programmatic interface? Do they have buttons and dials? Do they have a way to remotely access it? Right? What are the things that they can do? And how expressive are they? What can I do with them? Because there are times that you purposefully limit one of those interfaces. You have a secret button hidden somewhere to access a debug console, or you have a password somewhere that prevents the full access to the debug console that a repair technician might have, or something like that, right? So think about step one, you think about the customer interfaces, think about how expressive they are, and then decide whether or not that's sufficient for, say, Jenkins to work with those. The next thing is you think about what you can't do through a customer-facing interface. My example earlier, I can't, through a customer-facing interface, somehow plug in a USB stick. The USB stick in the front panel, that's a customer-facing interface, but I can't automate that. I don't know how to automate that. Let's get a bunch of cheap interns or something like that and just have them plug in USB sticks all the time. But then there's other things about that too, right? Like a customer-facing interface, we could think about customers in a different way. What about the repair technicians when something comes back? Is there a back door? How do repair technicians get console logs? If we have a failure in the field, how do engineers get access to debug information? Right? How do we help customers solve problems once it's already out there? There may be another interface that you can use. And if you wrap your head around it, those are just other types of customers once you've already shipped your product, right? However, there's also things that you cannot do, right? I can't plug in the USB stick. I can't effectively power cycle the instrument. I could tell it to shut down, but I can't push the button to get it to come back. I can't swap probes around. I can't change monitors or hook up other peripherals automatically like that, unless I virtualize that or spoof that somehow. Right? So really, the third thing here, when you think about the things that can't be accessed through some sort of existing interface, those are really your high-value things. Those are the things that you should think about when you're talking about minimum accessibility. What should I make an exception for from a customer-facing scope? Minimum accessibility will enable something called abstract communication. Abstract communication is effectively how we're going to get something like a continuous integration service to talk to the physical device. How am I going to get Jenkins to talk to the scope? It works with minimum accessibility because potentially this is one of the tools that the automation system is going to have to use. When I want to deploy a build to the scope, then I have to use SSH. I have used part of my minimum accessibility in order to do that. When I want to test, I can use something like a programmatic interface or something that a customer is going to use. The other nice thing about this is if I look at a system like Jenkins, Jenkins has kind of like this master server, and it has a bunch of nodes or slave processes, right? Different build servers and all this different stuff. If I use abstract communication, then I can actually pretend as though a scope is actually in this kind of build pool. I can put a scope in a test pool without actually having in the test pool. And the reason I would want to do that is because a system like Jenkins or others are really good at kind of load balancing or picking things to do tasks. So if I want to pick a scope to run a test, I can let Jenkins do all that for me. We accomplished that whole kind of abstract communication layer with virtual machines. You could similarly do this with something like Docker and containers. We chose virtual machines. And essentially what we do, what this kind of chart describes, is you have Jenkins, which communicates with these virtual machines. The virtual machines have configuration management from Chef, which means that all their configurations and things like that, all the tests and stuff, those are in version control, which is in Bitbucket. The virtual machines live in vSphere, vCenter, right? So that manages the whole hive of virtual machines. And to Jenkins, you would see a list of what would say scopes. Scope 1, Scope 2, Scope 3, Scope N, right? And in my lab, I have the physical scopes. However, the physical scopes are not actually nodes in Jenkins. The virtual machine is. And the whole point of having that virtual machine as a node in Jenkins is now all of a sudden I can do interesting things with the actual scope. So when I execute tests, when I do administrative operations like install a new build, when I want to power cycle things, when I want to do health checks on the scopes, I can do it all remotely from the virtual machine. And that's really great. Have you ever tried to power cycle a slave on Jenkins when it was in the middle of running a job? It's not really, it doesn't like that because you break the job because you've just reset the slave. So the nice thing about this is when I tell a virtual machine to power cycle one of the scopes, the virtual machine still is alive because the virtual machine doesn't need to be power cycled. The scope does, right? So this enforces a couple things. We get to exercise customer-facing interfaces. So my virtual machine can communicate with that oscilloscope just like a customer would. If you had one of these oscilloscopes, you could talk to it from your PC, right? Just like these virtual machines talk to it through an existing interface that a customer is expecting to have. We also get to extend kind of pre-test events into automated tests. So that seems kind of like a weird statement, but for the scope, for this instrument, I should be able to power cycle it. A customer should be able to reset it. They should be able to unplug it and plug it back in. They should be able to do stuff like that, right? By abstracting this layer of communication, having the VM tell the scope to do it, I no longer have to worry about a broken job chain. I no longer have to do anything. And I can actually write a test that represents that thing. So I don't even have to have a manual test that says, yes, I can power cycle the scope, because the automated testing can do that remotely. And then, of course, the virtual machines themselves can be encompassed in some configuration management tool. In our lab, we have something around 40 oscilloscopes in various configurations. We have Chef define what those virtual machines are supposed to look like. And the nice thing is that they're all kind of clones of each other. There's nothing really unique about them. They're just dumb, headless slaves. So it's really nice for a simple Chef recipe to be able to written to say what sort of test tools or what sort of libraries and things are supposed to live on that VM to be able to communicate between Jenkins and the scope. And we have just one single recipe that lives in version control that can do that. Abstract communication enables dynamically reconfigurable hardware. So this is a big deal for us because there are so many permutations that one of these devices could possibly be in, right? I have 40 in the lab, and there are millions of combinations of setups that I could possibly do. So being able to physically change something about the oscilloscope without touching the VM, without touching Jenkins, without doing anything with respect to automation or how that works, then I'm actually able to really quickly adapt to other configurations, right? If development needs a test, an edge case setup, or if they need to test some specific feature, or if we know that the next build that we're shipping out to customers only has some sort of special thing to it, then we can change everything about the lab very quickly, and I haven't touched anything in the code. All right, I haven't touched Chef, I haven't touched the VMs, I haven't touched Jenkins, I haven't touched the tests, right? That all works because we have this abstracted layer, because we have minimum accessibility. Here's a couple pictures of our labs. Every one of these scopes in these pictures are set up differently from the other. So the oscilloscopes themselves, these are mostly prototypes in some stage or another. And as I said, there's millions of possible combinations that they could be set up in. But I can't get the budget to test them all. They're not going to buy me that many prototypes. So I have to be able to make do with what I have. So the idea is that working with marketing, working with software development, you can try to make a picture of what is the most likely customer-facing device and have the lab set up in that configuration normally. And then as regression tests run, as field reports come in for defects, you can change any one of these scopes on the fly and continue running tests with little to no downtime. So as I said, you can test using the set of edge case configurations. You could facilitate kind of experimental hardware changes. You can swap out failing instruments when you're building something, when you're building hardware. Prototypes that fail happens, right? So I don't have a list of statically defined scopes that live in the lab because I have these VMs that represent scopes. So if one of them happens to die because it's a prototype, it's okay. I'll just get a different one and I'll put it where the hole was and we continue going as though it's no big deal. So if we assume some measure of risk, if you have to, you can enable minimum accessibility. You can do something like I did. You could turn on SSH to get access to some feature you wouldn't otherwise be able to get. If you do that, then you can get access to this minimum abstraction layer. Because I've done that, I'm able to have this VM represent that scope. And because I have a VM representation of the scope, I can now dynamically change things about that scope. I can change the test pool. I can do all sorts of stuff that don't actually have me recoding anything about my automation infrastructure. When you do all these things in concert, we were able to create a really kind of durable test environment that allowed the quality engineers, allowed development to make changes to that test pool, make changes to the software, and help debug issues in a way that the lab, that automation, was able to accommodate pretty easily. So if the development team or the SQEs had a request to change something, it could happen very rapidly so they could continue doing their testing. The lab and physical setup of it was not an impediment. So that's pretty much it. There's some references on the different tools and stuff like that, books on continuous integration. What questions do you guys have, if any? Oh, yeah.
So are all your checks end-to-end?
No. So there is different layers of builds. Builds are happening all the time. And we actually allow this kind of instrument pool, these 40 instruments, to perform various levels of testing. So we can do integration builds, which are maybe a smaller subset of tests to verify core behavior. We can do daily regression checks, which would be end-to-end. We could also actually allow engineers to take some binary that's already been produced and trigger the testing system with an arbitrary binary on some arbitrary setup in the lab as well.
On the machine itself, or is it all in
What do you...
I'm curious if there's another way to drive the test by driving the interface. That's just logic layer. It's below the do. You have the test screen doing it in the telescope. There's a lot going on behind it. Can you drive the behind parts of the software onto the telescope?
So there is a programmatic interface on a lot of these devices, which actually allows you to do a lot of things. And it is customer facing, absolutely. Yeah. Yeah. For a lot of things that's a main driver for automated tests. Obviously that has some limitations. Yeah.
And on failure, do you reproduce it in the lab?
We actually found, because there's a few different hardware configurations. There's different types of channels. There's different types of bandwidths, right? So we actually found, we gained more confidence from the development team and from the quality engineers when we actually tested a kind of a collection of instruments. So we create these artificial banks of 6 to 8 instruments, and then we'll run the build against that. And those are in various things. So if you get a test case failure on just one, that might be a red herring. But if you get it on a few of them, right? That's much higher confidence that something is actually going on.
Does anybody worry about the one-off failures in terms of the line? Could there be a deferment?
It depends. If there is something particularly special about the instrument that it has failed on, if it is somehow particularly unique, then it usually warrants some measure of attention and investigation. Otherwise, we can do things where we look for trends, right? If it fails again, or if we hit some threshold percent of failure, then we'll be interested. There's so many tests and so many instruments that we try not to get too bogged down for kind of sightings. We try to make note of them, document them, and then time box that task and come back to it if it still seems to be a persisting problem.
So, I was wondering if I could get an tell me about how many teams are sharing, so you have this resource, about how many teams are sharing it, and the combination, and about how many people you need to support the combination of Jenkins,
Yeah. So the team who developed that scope is approximately 80 engineers, geophysically separated. So we have engineers in Santa Clara, in Beaverton, in Bangalore, India, and they are all expected to be able to produce builds, execute automated tests, and inspect any of those instruments, right, at 24/7. We have a team of 2 who focus almost exclusively on kind of this DevOps portion of it. And then there's also a team of about, I'd say, 10 software quality engineers who also focus mostly on the testing aspect of it.
So about 10 people like using the data to test, use the data to test,
Using the data. So really probably only about 2 people who do pretty dedicated DevOps type work. So we actually have a couple mechanisms available because we have so many different consumers of this build system. It's a large, multifaceted product. We care particularly about what I'm going to call like a top-level build. It's a large application. Like I said, there's about 80 engineers who work on it. And they all work on subsets of the application. However, when they're ready to deploy their subset or submodule into this kind of mainline, then we actually use Git flow and Git branch naming conventions to trigger jobs in Jenkins, which will start the full, depending on the branch name, we will trigger some pathway of building, testing, deploying, etc. Just going a little further into that, functionally, our teams are assembled functionally. So you could have something like feature, function, Jira task or something like that as a branch name, and that's nuance. That means something to the build system, and it will perform specific tests, notify specific people, publish builds specific directories, target specific instruments. It'll do a lot of things based off of that Git branch name. Yeah. Yeah, so we decided that it would be better if the complexity didn't live in Jenkins. We didn't want Jenkins to decide which test should run on which scope, because that meant that Jenkins controlled too much, and Jenkins is an inversion control. So we push the complexity to the test. The test itself, the test runner, the test framework, and the tests themselves are the ones that decide The VMs have awareness of what physical setup the scope is in. And then when the tests execute, they gain some of that knowledge. So they'll know, do I have some sort of source hooked up to this oscilloscope? Can it measure something? Right? So we'll tell the test framework stuff like that. But then after that, it's up to the test to say, am I a scope? Do I have access to this? Do I have that license? Do I have this probe? Okay, test this feature. So a lot of the testing, a core chunk of the testing is behavior-driven development. For the behavior-driven testing, they actually the quality. I don't write the tests, so I'll talk about it. They use a Python test framework called Behave, and then have kind of built up off of that. And so that does use some tags, right? So you can do tags like the intensity or duration of testing. You can really kind of do anything you would like with the tags. They chose not to do too much. They kind of focused tagging on intensity and duration. However, in the behavior-driven testing style, Gherkin style, you can say things. It's an English format style test where you can say, given a thing, and I have a thing, and another condition, then I will do some stuff. That is where the gating conditions mostly live. The nice thing about that is that you can actually show the test to somebody who doesn't write tests. You can show it to marketing, and they go, yeah, that looks like that's what it's supposed to do. Yeah.
So you use Jira, Project, Confluence. You don't have to say anything bad about them. Is there something specific that makes it different?
I inherited it.
Oh, okay. I'm looking for a good argument.
I inherited it. I mean, we've made do with it. You could do neat stuff. Pipelines as code in Jenkins too, right? Like, which is great because that means all your job definitions get checked into version control just like everything else, right? Still has to pass a build, still has to pass a unit test, still has to prove that it's good just like everywhere else instead of editing a web page. So I mean, that in and of itself is pretty awesome. Anything else? Yeah. 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 Yeah, we actually thought about, we thought very long and hard about using something like Docker to kind of spin up a test environment that targeted the scope, because it really doesn't mean anything. It doesn't really have anything too unique about it that marries it to the physical scope. It's kind of just a dumb slave, right? That's kind of the point. The reason we did it is because they're always testing, and they're always running, and they're always available. And it was a way for us to kind of manage the physical instrument pool. So we can do things like, instead of destroying the container and it's just gone, you can say temporarily take the VM offline, which looks like taking the scope temporarily offline, and leave a note like this is physically in service or something like that, right? So you prevent Jenkins from using it. You also leave kind of a maintenance note for people who, when they go to the lab and they're like, why isn't this scope available for me? They have a note there that says why. That's probably the biggest reason, but I could absolutely see, being more efficient with our resources and having stuff like containers or just flyweights or whatever, managing stuff like that. I guess it's mostly just a preference thing. Anything else? All right, great. Thanks.